Hello, welcome to Chapter 5, Week 5 of Business Statistics Quantitative Methods. Today's lesson is about discrete distributions. So let's get started. So, the overall learning objective is to categorize probability distributions that produce only discrete outcomes, which means that you have a set number of outcomes. Roll of a dice, 6 faces only. Flip of a coin, exactly heads or tails. There is no third or fourth or fifth option. So discrete outcomes. It's either head or tails. It can't be 1.5 heads, zero point 0.3 tails. It is just heads or tails. So we will define a random variable in order to differentiate between a discrete distribution and a continuous distribution. We'll see what discrete and continuous really means. Determine the mean variance and standard deviation of discrete distribution. We'll solve some problems involving binomial distribution using the formulas and the tables. And then we'll have a look at Poisson distribution. We'll solve some problems for Poisson. We'll look at hypergeometric distribution and some problems related to that. So first of all, what is discrete versus continuous? So continuous is infinite precision. Let's say my age is a continuous variable. How old am I? 35 years, 2 days, 3 hours, 4 seconds, and I can go up till micro, nano, and even smaller seconds. So I have to stop somewhere. I say I'm 30 years old, or if somebody wants to be really precise, I say I'm 30 years, 200 days old, or something. But age or time is actually infinite. You can, between any two readings, you have another reading, and then between those two readings, you have another reading and another, and it just goes infinite. So distance, length of something, they're all continuous distributions. You cannot store them in a computer because computer cannot have infinite number of decimal places. So you have to make them discrete. And discrete means that you have to pick a number, or you have to pick a precision. You say, my precision will be after three decimal, up till 3 decimal points. So I want to measure this length in meters. So I say 5.397 meters. And that number you can store in a computer. So that is the difference between discrete and continuous distributions. Now, random variables is a variable that can contain outcomes of an experiment. For instance, one roll of a dice, if we store it in a variable, say dice roll outcome, then if you roll one right now, the next value of that random variable can be any one of those 6 values. It is a discrete random variable. So the number of heads on 10 flips, number of defected items in a random sample of 100, number of times you check your watch during the class, and so on. So that is discrete random variable. You have set number of options. Then continuous random variables are a random variable that takes an infinite value, which I just described. Increasing precision, infinite precision. For instance, time until a light bulb goes out, or height of a person. You can go into nanometers or even smaller meters or time scale. So you have to discretize random continuous variables. Okay. So this is a discrete distribution example. What does that mean? Remember in the class we talked about if you keep on rolling 2 dices and you keep on getting the sums, the highest number of times 7 will occur. Why? Because 7 occurs during most combinations. And 2 can only occur if one dice shows 1 and the other dice shows 1 as well. And 12 can only occur if both dices have 6 on them. So the chances of 2 and 12 coming are the least, and the chances of 7 coming is the most. So if you have a system that you say that it consists of two dices and I'm going to roll it millions and millions and millions of times, and we did this experiment in earlier, that we wrote Python code and we said, okay, I'm going to run this Python code for 10 million times. I'm going to count the number of times the sum of a roll was 2, 3, 4, 5, 6, 7 up till 12. And then we plotted and we saw that it is a very discrete distribution. Now, what is discrete about it? There is no 7.5. There is no 9.87. It's either 9 or 10 or 11 or 12. There is nothing beyond 12. Why? Because the system does not have a number greater than 6. You have 6 faces of dice, one dice, and 6 faces of the other dice. So the only possible sums are from 2 to 12. So that's why it's discrete. And the distribution, the shape of this number of times that you counted, that how many times does 7 occur, it tells you how the system behaves. So right now the system is telling me that 7 occurs most of the times. Okay, so imagine you roll 2 dice and add up the numbers on the top. You can get a total from 2 to 12. You can't get 2.5. So each column shows how many different ways you can get each total, and we see that 7 is the tallest. Now, discrete distribution is a way to describe the outcome of a system or experiment and how often or how likely each of those outcomes can happen. It is a map, it is intelligence or a table that you gain insights from. Each outcome must be countable, 0, 1, 2, whatever, right? So this is an example of a discrete distribution. So all of us on Google must have seen something like this. You want to go out with friends to a restaurant. You say, okay, let's see what that restaurant is like. So you open up, let's say you search Little Lebanon, which is a restaurant, and Google says, hey, this is where it is. You got the reviews, 3.9 stars, great. And then you see something at the bottom right, popular times, and it tells you by day. So today is a Friday, and this is how it has been busy. So this is the number of, this is the discrete distribution of the busyness or the popular time that this restaurant has been busy. So I see that between 6 and 9 p.m. it is the busiest. So if I want to go in that slot, I better book. But if I want to go 3 p.m. or maybe later than 9 p.m., I'll probably find a table so I can just walk in. So that discrete distribution of how popular or how busy Little Lebanon is tells you a story. So this is a discrete distribution of the busyness of Little Lebanon, and it tells people a lot of things. If you click a Monday here, the distribution would be different because everybody is in office, nobody goes out. Most of the people don't go out and enjoy their nights because they have to go to work next day or whatever they want to do. So the distribution for each day is different, but this tells you something. Okay, so that is another example of discrete distributions. Okay, so how do you describe a distribution? So it can be described by constructing a graph of possible probabilities of occurrences of different events or values, just like a histogram. So we construct a graph of the distribution, and measures of central tendency and variability can be applied. So we will study the central tendency and other characteristics of this distribution in the coming slides. So one of them is the mean. Mean, in simple terms, it's the average. 5 students get some grades in a test. Somebody asks you, what is the average score of the class? You add their grades together divided by 5, and that is the. So that's simple mean. There's nothing fancy about it. So mean of discrete distribution is the long run average. So if the process is repeated enough, long enough, the averages of the outcome will approach the long run average mean, which means just multiply each value with the probability. So xi is the ith possible outcome, or 7 is a possible outcome, 10 is a possible outcome, 4 is a possible outcome. So 4 into 0.8 plus 3 into 0.5 something plus 7 into 0.17 and so on. That is what we're doing here to get the mean. So you sum up all the probabilities of each outcome, you multiply, and then you add them together. Okay, so that gives you the mean of this discrete distribution. So let's say you have a system that can only have 3 outcomes, 0, 1, or 2. 0 is 20%, 1 is 50%, and 2 is 30%, or 0.3, 0.5, 0.2. So what is the mean of the system? This into this, plus this into this, plus this into this. So it is 1.1. And that is all that you need to understand. So any outcomes in a discrete system, and you have their probabilities, you can calculate the mean of that discrete distribution. Okay. Then comes variance, which is the second characteristic. So variance of the discrete distribution is found in a similar manner like you do it in normal raw data. Sum up the square deviation from the mean for each occurrence, subtract its value from the mean, take a square, multiply it by the probability. So that is the variance. Standard deviation is a simple square root of variance, and we've seen that earlier. So this is how we compute variance and standard deviation. Let's see an example. An executive is considering out-of-town business travel for a given Friday. Now that executive is the one who does all the crisis management in the office. So if something goes wrong, the manager takes care of that crisis. And he is afraid that when he's gone or she's gone, then if there's what is the probability that a crisis will occur? So at least one crisis could occur on the day that the executive is gone. Now the executive needs some past data. So if we get the distribution of the number of crises and the probability that each number will occur, 1 crisis, 0 crisis, 2 crisis in a day, then we can answer his question. For example, there is a 0.37 or 37% probability that no crisis will occur, a 31% probability that 1 crisis will occur, and so on. So let's say over the years, he looks at the data and say, out of the past 1,000 days, 40 or 37% of the days there were no crisis, and 31% of the days there was just 1 crisis, and so on. And there were very rarely in a day, only 1% of the days out of the past 1,000 days, say, you have 5 crises in a day. So if I go away for a day on a Friday, what is the probability that a crisis will occur? Okay. So we calculate mean, standard deviation, and discrete distribution. We know the crisis and its probability. 0 crisis occurs 37% of the times. 4 crises occur in a day 4% of the times. Okay. Let's multiply these two x and p's together. So this into this, 1 into 0.31, and so on. Add it all up. So it comes out to be 1.15. Okay. So this is the mean. Now, we know that the variance is really mean minus this. Okay. So what was variance? Mean minus this whole squared multiplied by the probability. All right. So let's compute that. So this is the distance from 0 minus 1.15, we get minus 1.15, and then we square it. When we square it and multiply it by the probability, this gives us the variance. And if you take an under root of the variance, you get standard deviation. So the standard deviation is 1.19. Okay, now we're getting somewhere. So we know that each probability has to be between 0 or 100%. And the sum of all probabilities should be 1. So if you add all these probabilities, you get actually 1. All right. So the sum of all probabilities will be 1. Now, these are some valid probabilities. These are invalid. And this is not, both are not valid. Why? So x value can be 1, minus 1, 0, 2, and so on. But the probabilities are always between 0 and 1, and their sum is 1. In this system, it's not valid because the probability cannot be minus 1 or minus in minus. It has to be from 0 to 1. And this system is invalid because the sum of probabilities is more than 1. Okay. So, coming back to this question now, what does this standard deviation tell you? It means that mean on the average, 1.15 error or crisis occurs every day. And then you have this standard deviation. So in the coming lectures, we will see how we can create a distribution, and then we can say this is the mean plus minus 1 or 2 standard deviations is 95% confidence. And then we will answer this question. Okay, so let's just put a pin in this right now and we'll come back to this later. Now, binomial distribution is another type of distribution. It is a discrete distribution where x is the number of successes and it follows 4 conditions. There are n trials. For example, n is equal to 20. You will flip the coin 20 times, or you will roll the dice 20 times. All trials are independent to each other. If the previous experiment you flipped a coin, you got heads, then it has nothing to do with the outcome of the next trials. They're all independent to one another. Okay, so independent and dependent is very important. And the outcome, there's only 2 possible outcomes. Okay, only 2 possible outcomes, or something. So either yes or no, true or false, passed or failed. There's no third option. That's why it's called binomial, because there are only 2 outcomes. So when you have questions like yes or no, true or false, pass or fail, then you ask this kind of, then you get into this kind of distribution. So probability of success is constant. Let's have a look. Where does binomial distribution, where is it used in real life? Remember, 2 outcomes only. Medical trials. A patient improves after taking a drug or not. Why it matters? It helps test how effective new treatment is. Second scenario is food quality control. Burger is correctly wrapped or not. It keeps customers' complaint low and brand reputation high. Online orders. An order is delivered in time or not. Imagine you ordering something on eBay and it arrives 20 days late. You're not going to be happy. So an order can arrive on time or not. There's no third option. COVID testing. Are you COVID positive or not? Game design. Player wins or loses a level. Customer service. Surveys. Customer is satisfied or not. So all these data points or distributions are binomial. It's either yes or no. So let's have an example. Let's say you have a coin and you flip it 10 times. X is the number of times you get heads. Now, when you flip a coin, there are only 2 options, either heads or tails. So now in this system, what is the binomial distribution of you flipping a coin 10 times? X is the number of successes, and we say that X follows, well, success means a head, let's say, and X follows a binomial distribution with n trials. Why is it binomial? First of all, n is equal to 10 because you will flip the coin not infinitely, but n number of times, which is 10. And the second criteria is this binomial distribution is only has two outcomes, heads or tails. And the third one is the next coin flip has nothing to do with the results of the first coin flip. So if the data follows a binomial distribution, then we can summarize the probability of head or tail. Okay. And this is the probability formula for a binomial distribution. N is the number of times that is the total number of trials. Okay. X is the number of successes you had. P is the probability of success, and then factorial, you know how to do that. So if you try to wrap your head around this, P means the probability of heads, and 1 minus P means the probability of not heads, which means tails. So if probability of heads is 50% or 0.5, then 1 minus P is 0.5, which is tails also has that probability. So you flip a coin 5 times and it is equal to 5. You want exactly 2 heads. What is the probability? And this is what this equation answers. If I flip a coin 5 times, what is the probability that I'll get 2 heads exactly? The chance of a head is 50%. Put that in the formula. So chances of getting exactly 2 heads out of 5 trials comes out to be 31.2%, 5%. So this is the kind of questions that people can ask, and you just give them the probability, and then you can use that in your decisions. Now, mean value or average expected result is really the number of times into the number of times you've gotten the head into the probability. So n is how many times you're likely to flip the coin, 10 times. So 10 into probability 0.5 is really 5. So you expect that 50% of the times head would come, and you know that if I flip a coin 1 million times, then 50% of the times I should get heads. Okay, so this is what it's telling you. Then we've got variance and standard deviation. So variance for binomial distribution is the number of trials or the number of times you will flip the coin multiplied by its probability and multiply by the probability of it's not coming. So 0.5 into 0.5 into say 10. And standard deviation is the square root of variance. So what is variance and bias? Let's have a look. This is really important to understand. Let's say you have a dart player and you have this board that you throw darts at. And if you have an excellent player, then that excellent player would always land very near to this red circle, okay, on the top left corner. So that's an excellent player. He's got very, very low variance. Very low variance means that all his points are really close together. All his throws aren't too far apart. On the right hand side, top right, you have a player which has very high variance. That player most of the times is away from the bullseye, but if you take an average, it's all scattered around the bullseye. And then you've got something called bias. Bias is, okay, a player can really throw well, but all his aim, he was trying to hit this red dot. So the variance is low, but there is bias in his throws. So he's off by a bias of some inches or something. But still it's pretty accurate with a bias. And this is high bias and high variance. So bias is high because most of them are in the top corner and then it's all over the place. So this is what bias and low variance means. We are talking about variance. So this and this, the top two. So using the same coin toss, if I toss it 10 times, what is the variance? 2.5. And what is the standard deviation? 1.58. So even though you expect 5 heads, you usually get something like 5 plus minus 1.5 heads. Okay, sometimes less than 5, sometimes more than 5. So let's do an example for binomial distribution. According to US Consensus Bureau, approximately 6% of all workers in Jackson, Mississippi are unemployed. So we have 6% unemployment rate in Jackson, Mississippi. It's a city. So 6% unemployed, and you want to conduct a telephone survey in which you will call 20 people, and you want to find out that if I call 20 people, what is the probability that 2 or fewer unemployed workers would be there. So out of those 20 people, I will get 2 or less than 2 people who are unemployed. Random survey. So let's think about this for a minute. There are only 2 outcomes of each experiment or each call. Either the person is unemployed or the person is employed. So that's binary, or that's one thing. The second one, you have fixed number of trials. You have 20 number of trials. So n is equal to fixed over 20. And the third thing is that it doesn't matter if you randomly call somebody and is not unemployed. It doesn't mean that the next person you call will depend. His employment will depend on the past trial. So it's very independent. So binomial distribution is warranted. Fixed number of trials, 2 possible outcomes, constant possibility of success, and they are independent trials. So this confirms that the problem is approximately modeled by binomial distribution. So let's do it. The probability of being unemployed, P, is 0.06 or 6%. Not being employed is 94. Employed is being 94%. 94 plus 6% makes up 100%. Your sample size is n. X is the number of successes desired. You want 2 or less than or equal to 2. So the hard part of this problem is finding out P, N, and X, and you have them. So put it in the formula. X would be 2. So this is the probability of exactly 2. This is the probability of exactly 1. This is the probability of exactly 0. Okay. And if we add all these 3 probabilities, the probability of getting nobody unemployed in the 20 calls, 1, 2, if you add all these probabilities up, you get 88.5% confidence or probability that if you call 20 people, 2 or less of them will be unemployed. What are the mean and standard deviations for this distribution? Simple, n into p. So that's 1.2 is the mean, and standard deviation formula is this one. So 1.062. Now what we do is we say, okay, we can just create a table once, and then we'll just use that to look up probabilities. So x is equal to 0, 1, 2, 3, 4, 5, 6. If I call 20 people and all 20 of them will be unemployed, these are the probabilities. Okay, if I have 6% unemployment, 7% unemployment, 5% unemployment, and so on. So I work out that table, and then I don't have to use the formulas. I just say, okay, what do you want? 6% unemployment. If you call 20 people and you want 2 or less of them to be unemployed, this 2.22 plus 0.37 plus 0.29, add it all together and you will have your answer. Or if you want to say exactly 4 of those 20 will be unemployed, it's 2% chance. So this table helps you decide what very quickly what the answer is. And you can do this in Excel as well. This is the Excel's binomial distribution formula. You have 2 columns and you just calculate n and p, and it does it for you. Similarly, Minitab can do the same. It's a statistical software, and you can just use that, but Excel is pretty decent. The next one is Poisson distribution. And the main difference between Poisson distribution or binomial distribution is that you don't know how many times the event will happen because it's not in your controls. So, you want to say, how many times does lightning hit um, in Australia in a year? Okay, or 3 years or 10 years. Now, you can't order lightning to hit 20 times and then look at the results that it hit 20 times. How many times did it start fires? You can't do that because it's not in your control. So Poisson distribution was actually um, invented to model that. It focuses only on the number of discrete occurrences over a specific interval of time or length. So Poisson does not have a given number of trials as binomial experiment does. Occurrences are independent of each other. Again, occurrences are independent. And they occur over an interval. So you choose an interval. So how did that start? It was actually started in 1837. It was used in 1837 by Denis Poisson to describe the probability of very rare events occurring certain number of times in fixed time intervals. And at that time, the interest was analyzing how many soldiers were kicked to death by horses in the Prussian army. So I know it's not interesting, but they were interested. So if you move an army, how many soldiers will be kicked and killed due to their own or others' horses kicking them? That's a rare event. Nobody usually hears about horses kicking people, maybe by accident or maybe the horse goes crazy or whatever. So Poisson was for rare events to start with: horse kicks, bomb strikes. In the Second World War, it was used to predict that on this piece of land, what is the probability of bombs hitting here, and so on. Today, it is used to model events counted in a fixed time interval or a space interval. Rare or not, it doesn't matter now. As long as the events are independent, they are randomly spaced, and we don't know the number of times event will occur. We just know that let's look at 1 year and see how many times lightning strikes and so on. So where is it used? Power failures in a city per year. You can't predict a power failure. You can't ask a city to do 10 power failures. You just study it per year. Independent, unpredictable, discrete, and very rare events. Then customer arrivals at a bank per hour. Customer arrival is not rare, but you don't know how many customers will walk in the next hour. You can't control that. So although it is not rare, it is very random and time based. So you say in 1 hour, how many customers walk into this bank? Or from 12 p.m. to 1 p.m., how many customers walk into the bank? Why? Because you may want to hire enough people to cater for them. So it is not a rare event. Then meteoroids hitting Earth per year. It is a random event. So those big rocks, they just enter Earth's atmosphere. They usually get burned by the friction, but some of them make their way to Earth. But it's very, very rare. Typos in a printed book, you don't know how many typos there will be. Somebody publishes a book, there may be 1 typo, 2 typo, 3, whatever. So it's rare. Then calls to a tech support center. From 2 p.m. to 10 p.m., how many calls do you expect in a call center? It is not rare. They get calls all the time, but these events have to be, if you want to model them, you use a Poisson distribution. Then disease outbreak, website hits per minute, not rare. You want to predict it or find it or model it so you can have an appropriate server sitting at the back. Then bomb hits in a war zone grid. It's very rare. So World War II, Poisson application was very famous in predicting this. Now, if Poisson distribution is studied over a long time, a long run average can be determined. So the average is denoted by lambda. Each Poisson distribution contains a lambda value, which is the average from which the probabilities are determined. Poisson distribution can be described as lambda alone. Okay. And here is the formula. The probability of an event happening is really lambda raised to power x, where x is the actual number of events, and epsilon, or the Euler's number is 2.718 raised to power minus lambda over factorial of x. So lambda is the long run average. We know the value of E. Okay. In this case, mean, variance, standard deviation is all lambda. Variance is lambda, mean is lambda, and the under root of variance is actually standard deviation. So it's pretty easy to calculate the Poisson distribution. Let's do an example. You are at a bank and you want to see if the average customer arriving, the long mean is 4 customers per hour. 4 customers arriving per hour, that's the long-term mean. So the mean is 4, variance is 4, standard deviation is 2. This means that the number of customers per hour is usually around 4, give or take 2, because the standard deviation is 2. So if you go with 1 standard deviation, and we'll talk about that later. So bank customers arrive randomly on weekday afternoon at an average of 3.2 customers. So lambda is 3.2, mean is 3.2 every 4 minutes. What is the probability of having more than 7 customers in a 4-minute interval on the weekday afternoon? So let's calculate that. We know 3.2 customers per 4 minutes. We calculate the probability that x is greater than 7 customers per 4 minutes. So the probability of x greater than 7 is really equal to 8 plus 9 plus, or we can say 1 minus probability of less than and equal to 7, which is 7, 6, 5, 4, 3, 2, 1, 0. So this is what we do, because the upper one is impossible. You want to go till infinity? You can't do that. But you know that 100% of the times minus 7, 6, 5, 4, 3, 2, 1, 0 is all the rest of the probabilities. So with lambda 3.2 and x 8 or 9 or 10 or 11, this is how you find the probabilities. And this answer indicates that more than 7 people would randomly arrive in 4 minutes, only 1.69% of the times. So bank officers should use these results to make staffing decisions. Okay. So this is the Excel version of Poisson distribution. Poisson is the function name. You give it the variables and everything and the lambda value, and it just does it for you. Similarly, this is how we do that in Minitab, but Excel is a better tool, in my view. The third one is hypergeometric distribution. Now, the hypergeometric distribution is also a discrete distribution. Each outcome consists of either a success or a failure. Okay, so binomial. Sampling is done without replacement. Sampling is done without replacement. Now that means that if you have 10 things or 10 marbles in a bag and you pick one, then now you have to pick from 9. And if those are different colored marbles, then the distribution or the probabilities of picking one color as compared to the other change if you don't replace the marble that you took out. So, and we discussed this in the earlier lectures as well. So sampling is done without replacement. Population N is finite and known. The number of success in population A is known. Binomial is an acceptable approximation of hypergeometric if number of candidates that you've selected is less than 5% of the total value or the total population. Okay, lots of words. So what is the main difference between binomial versus hypergeometric? What is the difference? Number one is replacement. In binomial, we put items back after each trial. In hypergeometric, you don't put items back. Okay. So the probabilities change after each choice or each trial. The probability stays the same. For binomial, yes, the chance of success is constant. The probabilities don't stay the same for hypergeometric distributions. So the third one is trials. Binomial, the trials are independent. But in hypergeometric, the trials are dependent. Imagine that you have a big box and it has white and black marbles in them. 5 black marbles, 5 white marbles, and you randomly just pick out one. It happens to be a black marble, and you take it out. Now 9 are remaining, but out of those 9, 4 are black, which are left, and 5 are white. So the distribution or the probability of picking a black marble as compared to a white marble and vice versa has changed, because in the first trial you took out a black marble. Let's say in the first 5 trials you take out all the 5 black marbles. Then the next trial is totally dependent on the previous trials because there are no black marbles left. 100% of the times you will get a white marble in the 6th trial. So the trials are actually dependent to what happened in the past or previous trials because you're not replacing them back. Common example is tossing a coin 10 times. You toss a coin, you say heads or tails, toss it again. You're not taking the heads out of the coin. And then drawing a card from a deck without replacement. So let's say you have 4 suits, heart, spades, diamonds, and whatever the 4th one is. And you say, I'm going to draw 1 card and I'm just interested in suit. If I, out of 52 cards, we have 13 cards per suit. If I take out a spade, then I only have 12 spade cards left. So the probability of getting another spade has reduced. So that is a common example. Then population sizes. In binomial distribution, you don't need the population size. In hypergeometric distribution, it is always fixed and known. The formulas used for binomial are based on combinations with fixed probability. But in case of hypergeometric, they are based on combination on population without return, which means it keeps on changing the probabilities. So here is the formula for calculating hypergeometric distributions. Okay. N is the population size. So N is the total number of possibilities or people you have to choose from, or marbles in a bag. And from those people or marbles or population, you will select N samples randomly without replacement. A is the number of success in population. X is the number of success in the sample. Okay. So in a population, let's say there are 48% males and 51% females. If you select 20 of them, which is N, then what is the distribution of males and females in that sample? So this is what the last 2 points means. So this probability of X happening is really ACX, which is ways to choose X successes from A total successes. Okay, so if a population has 4 males and 6 females, then there are 4 ways in which you can choose out of 10 or more. Okay, a male. N is the total number of population minus ACN. Okay. So ACN, this N minus ACN is the ways to choose remaining failures from the rest of the remaining lot, and NCN is the total ways to choose N items from a population. So you had 10 people, you choose 1, now 9 are remaining. You choose 1 more, 8 are remaining, and so on. Okay. How do you calculate the mean value? the number of successes in the population, multiply your sample size, divide by the total number of sample size population. Similarly, variance is calculated using this formula, and the square root of variance is your standard deviation. C stands for combinations. So N combination R. N combination R means ways to choose, or A combination C means the combinations or the ways to choose X successes from A total successes. Okay. And this combination formula, we just wrote something here, you don't know what that is. That is actually, if n combination r, then n factorial over r factorial into n minus r factorial, and that's how we do it. So you just put the n and r numbers in there and you find the combinations, the possible combinations that exist. For example, let's say you want to compute 8 combination 3, or the ways or the number of ways to choose 3 males from 8. Okay. So you have 8 males. What are the combinations of different males? Exactly 3 that you can choose from those 8 males. Put it in the formula, 56 different ways. Okay. In a population of 8 males and 16 females, what is the chance of choosing 3 males and 2 females? Okay. So first of all, x is equal to 3. Let's say what is the probability of choosing 3 males? Put it in the formula, 8 and 3, and you say 15.8%. Remember, the total population is 24. 16 plus 8 is 24. So that's what you have here. So it's 15% of the times you will get 3 males. So these are different combinations out of those 8 males. That 15% of. Okay. This is how we can use hypergeometric function in Excel. Hypergeometric distance, geom distance, and similarly Minitab has the same. So where is it used? It's one of the few distributions where probability shifts with every draw, just like real life when you're picking without replacement. So geometric models are exact, which makes them better than binomial in many small sample situations. So you have a small sample, you go for a binomial distribution. It is used in every casino where designing fair odds in games like blackjack, poker. So in poker, once a card is dealt, it's gone, and then you wait for the next card, so the probability changes. So quality control in manufacturing. You pick 10 items from a batch of 100 to check the defects. It helps company decide whether to accept or reject the entire shipment. Genetic research, selecting gene pools with certain traits from a DNA pool. Audit sampling and accounting. You can't audit all of the people. So you say, I'm going to pick 50 different samples from my 10,000 or whatever samples, and I'll do that. Medical trials. Selecting patients with specific traits for a study pool. Card games. Ecology. Wildlife sampling. Cybersecurity intrusion detection, used to evaluate the presence of anomalies when the data set is huge. Political polling. So picking random votes, voters from known district, and so on. Okay. Now, the question is that which distribution should you use? Binomial, hypergeometric, or Poisson? So ask yourself the questions. Are you counting success and failures in fixed trials? Binomial is your answer. Are you sampling without replacement? Hypergeometric is your answer. Are you counting events per time or space interval? Always Poisson. Okay, if we don't know the number of trials, Poisson. Does the probability stay constant? Binomial or Poisson? Is the event rare but ongoing? Poisson distribution. Is the sample size small compared to population? Binomial if it is replacement. If less than 5% of the population is sampled, binomial can approximate geometric, otherwise not. Okay. So this is the end of today's lecture, and please try the examples um, that are shared in the post-class activities, and I'll see you all in the next class. Thank you.